Good morning, Professor. Good morning to everyone.
Hello, good morning, Paula. So do you hear my voice?
Yes.
Yeah, okay, great. Because as usual, sometimes it happens that you guys don't hear my voice. So then I would just continue our lectures without any voice from your side, But anyway, now you can hear my voice. Okay. Okay, so I think maybe it's already 3+8, and maybe we can continue our lectures right away. Okay. So before we start our lecture, so I wanted to see my slide on your screen.
Yes, Professor.
Yeah. Okay. Okay. So maybe we'll just continue our lectures, since I think some of you have already joined our course. Okay. So okay. So make sure this. So good morning, everyone, and today is another week, and we are continuing our lectures on the pre-calculus. So I think last week we have introduced some polynomial function and the rational functions, and I believe that you all may know how to operate or to do some calculation or some operation with the polynomial function and part of the rational functions. And today we will continue our lectures on the rational functions, which we know how to graph out the rational functions, and then some of the operation with the rational functions we need to be to be careful to operate with this the graph of these rational functions. For example, if you still remember that we learned some of the asymptotes of these the rational functions, or in the the rational functions, which they well from certain of these properties. For example, if we approach into this in the rational function, if you still remember in last week, and we know the rational functions will start from this one of the x substitute one substitute of x here, for example. And in that case, you know x was in the denominators, which that will not cannot be equal to 0, right? So in this case, you can see the graph, they will have certain of the property that when the x approaching to the infinite or approaching to the 0, so they will have some kind of ability. It depends on how you define the function f of x, right? So you can see if the x approaching to the infinite, so you can imagine that when the x is approaching to infinite, which that will show that 1 divided by infinite here, okay? Which that means you can see they are very large in the denominator. So 1 divided by the very large numbers of denominators here, then you will see that this function will approaching to these zeros, right? And in the case of the x approaching to the zeros, or you can see a 0.001, for example. So you can see that could be 1 divided by the very, very tiny of the numbers in the denominators here, which that will be to the large numbers here. Okay, so you can see that when the x approaching to these zeros and the function f of x will approaching to the infinite. Okay, so you can see the graph will looks like this term. Okay, so that's some basic analogy with these rational functions. Okay. So as we learn some functions and start with this the graph of the functions, and also the graph of this quadratic function and also the polynomial function, they all give some of the information from the graph here. So from this graph, they can help you to understand the certain of the function. And also if we explain that in many of the real situation or some physics phenomena, they will all using a certain of the model to present the phenomenon or physics phenomenon of this physics, right? So from the graph, you can I believe that you can estimate or the phenomenon of these the physics or some of the real situation in our life here by the graph of these the functions. Okay, so this is just what we learned that last week, and the rational functions which that combine with this p of x divided by g of x here, where the p of x and q of x are the this q of x. Okay, sorry, and these two functions are the polynomial functions. And if you still remember that polynomial functions, they the definition of the polynomial function, they include an times of xn n power of the n. Sorry, just an and times of the x power of the n and plus of the an subject 1 power x power of the n subject 1, etc. to the a1 x and plus of the a0, right? If you still remember that definition of the polynomial functions, which they have some of the characteristic of the polynomial function. For example, they will have the leading terms and the constants with the independent variables, and also with the constant term here. In the case of the polynomial function here, the an cannot be zeros, and also the n cannot be zero as well, which that will lead to the different degree of these polynomial functions. And in the leading terms here, they also include some information or some coefficient. For example, the an is called the leading coefficient, right? And also the n is the represent the degree of this polynomial function, which these two information or these two constant or these two coefficients, they will let you know the degree of this polynomial function, which that will let you know that the terms of these polynomial functions or the end behaviors of these polynomial functions by the numbers, by the definition of this coefficient and the degree of this function here. Okay, so these are some basic knowledge. So now since we learned some rational function, they included the p of x divided by the q of x here, which both these are the polynomial functions. So I think the rational function just doing these divisions of these polynomial functions from the numerator and the denominators here. And if you still if you still remember some of the rational numbers, or the some rational numbers here, which they will have the certain of numbers in the numerator and some of number with the in the denominators. In some cases, they will have some of the factors could be or some numbers could be factoring out, and then you can cancel the common of the factors in the both of the numerator and the denominators. This is the same of the polynomial functions. But in the case of the rational general of the rational functions, we assume that the p of x and the q of x have no more of the factors in common, which they will have the final of these rational functions. But later we will also learn some if we have some of factors exist between these two, and then how we operate with these rational functions. Okay. So as we learn the rational function, we take this the most of the basic example, which is the f of x equal to 1 divided by 1. Okay, what x 1 divided by x here. Okay, and just as we explained, if we have this function, we can try to estimate the end behaviors of these functions. For example, when x approaching to the infinite, then f of x will approaching to the zeros. When x approaching to the zeros from the right hand side here, right hand side of the zeros, and then the f of x will approaching to the infinite here. I think that's to put simply from this the function here. You can I think easy to understand why the f of x will approaching to the infinite and approaching to the zero when the x approaching to the from the zero positive and from to the x to the infinite. Okay, and also the same as from the negative part here. For example, when x approaching to the negative infinite, which is in this direction, right? Then the f of x will approaching to the zero as well, which you can see that 1 divided by x. And also this will, if that is to the x approaching to the negative infinite, which will equal to 1 divided by negative infinite. You can also imagine that is a minus term, 1 divided by the infinite here. So this term will approaching to the zeros. Okay, so you can imagine that when the x approaching to the negative infinite here, the f of x will approaching to x as well. Okay, and the same as the x approaching to the zero negative, which to the right hand side of approaching to the x zero from the left hand side, the x of x will approaching to the negative infinite here. Okay, so that's what we learned in last week. And also here are some of the behaviors of these the rational function, and also the vertical and the horizontal asymptote of this the rational functions here. And if you still remember where to find the vertical asymptote and the horizontal asymptote, which the vertical asymptotes we know the r of x has the p equal to the p of x and divided by q of x, right? And also when we learn some polynomial function, we know we could factoring out with some of the factors and also find the zeros of this polynomial function, right? So since in the rational function they are combined with this polynomial function in the numerator and the denominator, so we also could both with the factorings of this function, which they will equal to x up to a1 times of x subtracted to a2, etc., and so on. Okay, and also in the denominators, they also could factor in out of x up to b1 and x subtracted to b2, etc. here. Okay, so then we could factor in out. So the vertical asymptotes was happening when the x cannot be when the denominator cannot be zero. So in this case, you can know that when we would like to find the vertical asymptotes, they will find this when the x cannot be equal to the b1 and the x cannot be equal to b2. Since when the x is equal to b1 and the b2, that will let this denominator become to zero. So as the vertical asymptote definition, which that will the functions will approach into the vertical asymptotes, or the function will approach into the asymptote, but they will not intersect with these asymptotes, both the vertical asymptote and also horizontal asymptote. So you can see when the x equal to b1 or x equal to b2, then we will find these vertical asymptotes, and that will define that the vertical asymptotes term here. So if you would like to find the vertical asymptote, just simply like these denominators terms zeros to find the zeros of the denominators, and then you will define the x point on the graph of these asymptotes, at the graph of these rational functions. Okay. And also the same as the horizontal asymptotes, we simply know that that will be some numbers with the y equal to certain constant numbers here. But that also could find that from these asymptotes at the numerators become to zeros. Okay. So as we mentioned that the rational functions was a vertical asymptote where the function is undefined, and where that the denominators is zeros. That's the one to present the find the denominators zeros. Okay. Okay, so then we understand the rational function is p of x divided by the q of x, right? So you can find that they are some of the polynomial function, and then we can find the transformation from the y equal to 1 divided by x. For example, you can see that the rational function can using the graph of this rational function. If that is the rational function with the sum of p of x that divided by q of x here, and then you can do in this graph of this rational function by shifting or stretching or the reflecting of graph of the function f of x equal to 1 divided by x here. This just would like to shows you the since we know the basic of the graph of the function 1 divided by x here, which will looks like this, right? And then if you still remember what we learned in chapter 2 regarding the shifting, stretching, or shrinking of the graph of the polynomial function or the functions. Then when we apply this the rational functions with the several terms, for example, like ax plus b and divide by the cx plus d here, so you can do in the certain of the shifting of this graph and also the stretching of this graph here, which they may well looks like this or even with this term. Depends on how you define the rational functions. Okay. For example, if you see that f of x equal to the 1 divided by the x subjective 3 here, okay, for example, this is also the rational functions, and this could be presented the a or 0 times of the x plus 1 and divide by the x subjective of 3 here. Okay, so you can see that it could be the function 1 divided by x subjective of 3. They also could present that in the 1 divided by the x subjective of 3, where the x position or the figure positions will be the right hand will shifted to the right hand side with the 3 units of these functions, which we can understand that the function of this term. Okay, so we also give some example last week regarding this rational function r of x equal to 2 divided by x subjective of 3, for example. Since we learned the f of x equal to 1 divided by x here, right? And then we could express this rational function in terms of x here, which that will equal to the 2 factor of the 2, which in terms of the 1 divided by x subjective of 3 here. Okay, so in this case, if you still remember f of certain numbers, they have certain of these 1 divided by this number here. Or we can review back of the functions. Where do we have the input of the x? And they have the machine box, right? and then they will have the output f of x here. Okay, so we know that we have certain of the independent variable, and then they will form a function, right? So then we know the function, they have certain of the functions in with this the f of the number or f of the square here. Okay, so since we are learning the f of x equal to 1 divided by x here, so in this case you can see that this could be presented as the box here. So you can see this will be shown in the r of x will equal to the 2 times of the f of the x subject to 3. And since we know the f of x equal to 1 divided by x, so in the case of the 1 divided by x subject to 3, then that will be shown that equal to the f of the x subject to 3 here. Okay, so then we know that the functions or the graph of these functions will be the graph of the 1 divided by x with the 3 units shifting to the right hand side. Okay. So this is why we learned that they found these the rational functions, and with the graph of this function, we just simply to doing this shifting, stretching, and also reflecting of this the function of the 1 divided by x here. And as long as you understand the operation with these the functions, okay. And also this also gives some informations, and since that function will r of x equal to the 2 times of the 1 divided by the x subject to 2 here, right? And since we know the function, the denominators, if we find the domain and the range of these functions, and since we know the x, this term is in the denominators, so the x cannot be equal to 2, because they will like this because I think this will when x equal to 2, and then the x subject to 2 will equal to 0, which that this 1 divided by the x subject to 2 was not exist. So you can see that so in this case, so this will be the rational function. So in the case this x equal to 2 is not defined that in this function here. Okay. So you can see that the factors, the function of x has the vertical asymptote when x equal to. Okay, so this sorry, this will be 3 in this case. Okay, so this will be 3. So be 3 here. So you can see the rational function has the vertical asymptotes of x equal to 3, and the horizontal asymptotes, which the y is equal to 0. Okay. Simply know that there is no of the variable in the numerators, so that will be the functions of this the horizontal asymptote will be the y equal to 0. Okay, and this is the graph of these functions. Okay, so we can start from this f of x equal to the 1 divided by x, and then they will start from here, right? Original functions, they will be looks like in this region. Maybe you can use another colors. So original this function of f of x. Okay. Okay, so then the function of the 2 times of the 1 divided by this also will equal to the 2 times of the 1 divided by x subject 3. So you can see that the graph, the asymptote will move from the 0 to the 3. Okay. So we can see the vertical asymptotes will be at the x equal to 3. Okay. And then you can see the graph of the 1 divided by x3. So they were similar like this rational the graph of the rational function, which that will 2 times of the f of x, 1 divided by the x here in this case. So you can see a little bit stretching of this graph. Okay, so and also if we would like to find the domain and the range, and since we know the domain will related to the x regions, and the range will be donated to the functional f of x. So you can see in the definition of this rational function, which the x could be any of the real number but not equal to 3, since there is the vertical asymptotes at the x equal to 3. And also furthermore, if the x equal to 3, that will let these functions become to no exist. When x equal to 3, that will let this denominator equal to 0, which is not existed in these functions. So you can see the domain of this function will equal to will be x cannot be equal to 3. And also they have the horizontal asymptote at the y equal to 0, right? So they also in the range of these functions, also the y cannot equal to 0 in this case. Okay. So here are some definitions we learned last week as well regarding these rational functions. And since we know the rational functions, they have the combination with the polynomial function, with the p of x divided by q of x, right? So then from this polynomial function or from this rational function, we know when we find the vertical asymptotes of the r, we just find the zeros of these denominators. Okay. In the case of the horizontal asymptotes, we know the degree of this polynomial function in the numerator and the denominators. When the degree of the numerator is less than the degree of the denominators, and then the horizontal asymptote will y equal to zeros. Okay. And in the case of the n equal to degree of the numerators equal to the degree of the denominators, and then the horizontal asymptote will y equal to the leading coefficient of these numerators and divided by the leading coefficient of the denominators. And in the case of the n larger than m, then the function has no horizontal asymptotes. Okay. Because later they will introduce another type of the asymptote, which is the slant of the asymptote, which they will doing this certain of the slant of the asymptotes, which the graph will be similar like this or similar like this. Okay. They all have certain of physics now, but later we will define of this other type of this asymptotes. But I think from the horizontal asymptotes, you can use in this the degree of these denominators and numerator to define the horizontal asymptotes. Okay, so with the graph of the rational functions, and I think that the graph of this function, just like other type, just like the graph of these functions here. For example, we here are some the step of this graph of the rational function. Firstly, we also using the factor to find the factors of these functions. And in the case of the rational functions, since they have the numerator and the denominators polynomial functions, so then we also doing this factor of the polynomial function in the numerator and the denominators. And once we know the r of x equal to the some number a1, x subtracted a2, etc., and divide by the x subtracted of the b1 and the x subtracted of b2, etc. here. You just factoring out of these polynomial functions. And then the second step was find the intercept, and as the graph of these functions, which we find the x-intercept, we let this y equal to zeros, and also when we find the y-intercept, we let this x equal to 0, right? When we find the x-intercept, usually we let this y equal to 0, right? So since we know the r of x equal to the p of x divided by the q of x. And we find the factors cannot be like this y equal to zeros, right? If we would like to find the x-intercept, so then we usually would like this y equal to 0. And in this case, the rational functions, the denominator cannot be zeros, right? So we just simply know we like this p of x, which is the numerator of these rational functions, become to zeros. And then we could find the x-intercept at this certain point when the numerator's term will equal to 0. Okay, so then if you would like to find the y-intercept, which that the y-intercept at this point here, right? Which simply like this x equal to zeros. And the y-intercept was happen in the x equal to 0 in this term. So that's the general step of the functions, or even with these the polynomial function, and also even with the functions. Okay. Then the next step is finding the vertical asymptotes, which that is the zeros of the denominators. Okay. And then when we find the vertical asymptotes, and then we quit trying to find the end behavior of these the functions. For example, we like this x when x approaching to the infinite, and also x approaching to the asymptote numbers here. Okay, and see what the function f of x will happen. Okay, for example, when x approaching to the infinite, then the function will approaching to the zeros. When x approaching to the zeros, and then they will approaching to the infinite here. So then you can simply to sketch out these functions, but they could be from the different of this direction here. It depends on the definition of this function or rational function. Okay. And then we next step find the vertical asymptote, and also we can find the horizontal asymptotes. We're finding horizontal asymptotes, and we are using the procedure that described in the box on the graph of this slide. Okay, just like the as we shown the these the tables. Okay, the horizontal asymptote, we just compare the degree of this the rational functions in the numerator and the denominators. Okay. Okay, so this just shows you that when the n, we know that when the degree of the n is the larger than m, when n is smaller than m, so the y will equal to 0. N equal to m, and the y will equal to the an divided by bn. When the n larger than m, so there is no horizontal asymptote. So that's the 3 step to find the horizontal asymptote. And then we could using some of the informations, and for example find some tables f of x, and to find some point here, and to sketch out the graph of these rational functions. Okay. Okay, so here we give an example of the rational functions, and graph it out of the rational functions, and state its domain range here. So following the step as we explained that in previous slide, and first step is factoring of this function in the denominator and the numerators here. So after we doing the factoring, so assume that this is quite easier to find out the factor, right? Which the factors, the function will factoring out of this the rational function could be factoring out this form, which will equal to the 2x subtracted 1 times of the x plus 4 in the numerators, and the x subtracted 1 and times of the x plus 2 in the denominators. Or I think that's quite simple to find it here. For example, in the case of the numerators, which now we'll see that 2 times of 1 And since that is 7 here, we just assume that will be 1 times of the 4 here. In the case that will be the positive 7, and this will be the negative sign here. Okay, so you can assume that this will be the positive, and this will be the negative here. So you can simply know that this negative 1 times plus of the 8 here, which will equal to positive 7 here. So you can see the numerator could be factoring out of the 2x subtract 1 times of the x plus 4 here. Okay. And in the case of the denominators here, you also could use in this time these methods, which 1 times 1, and also this will 1 times of 2. Okay, so then since that is the minus sign and this will be positive, so we will like this 2 will be the positive, and this 1 will be a negative here. So then minus 1 and plus of the 2, which will equal to 2. This will equal to 1 here. Okay. So that will quite be satisfied with this polynomial function, which then we will find the factoring of this term will equal to the x plus 1 times of the x plus 2 here. Okay. So then we could factor in of these rational functions as shown here. And then next we find the x-intercept. And from the x-intercept, we simply let this numerator become to 0. So we can see the x-intercept will be at the x equal to, when this equal to 0 and this equal to 0, which will find the x equal to the 1 divided by 2. And also when the x equal to 4 will be the zeros of the numerators, which that will be the x-intercept at this 2 point here. Okay. And then next step is the y-intercept. Okay. The y-intercept, we just simply like this x equal to this. Find the y-intercept. Okay, so we like this x equal to 0. So we simply know that y of the zeros, this will equal to the 2 times of the zeros squared plus of the 7 times of 0 plus of the subtrate of 4 on the original term. And also in the denominators will be a 0 squared and plus of the zeros and the subtrate 2. So we know that these are all when x equal to 0, so they will cancel. So then it will be equal to the minus 4 divided by minus 2, which will be equal to 4 divided by 2. Then we will equal to the 2 here. So the y-intercept will at the y equal to 2 here. Which we know that after we know the certain of the information, for example, the vertical asymptote at the this will be minus 4, and also the 1 divided by 2, and also the y equal to 2. So we can see the graph will be located at this vertical as horizontal asymptote and the vertical asymptotes at this certain point here. Then you can still imagine that the graph will more or less will looks like this term or this term. And also in some case they were from here, and also they were from here. But it depends on how you define the rational functions. Okay. Okay, so the y-intercept as we find is at the y equal to 0. Y equal to 2. Okay, in this case. And then the vertical asymptotes. As usual, we find the vertical asymptotes. So let's not define that. It's just so like to show you the intercept of these 2 points here. So maybe this is not correct for this term. So erase it here. Okay. Because we find the x-intercept and the y-intercept, and then we find the vertical asymptotes. We know the functions of x equal to the 2x subtracted 1, and also the x plus 1 here, right? Plus 4 divided by the x plus 1 subtracted 1 subject 1 and times of x plus 2. Okay, so that's the functions. And we find the x-intercept. Well, at the x equal to 1 divided by 2, and also the x equal to -4. And the y-intercept will at the y equal to 2. So we find that the graph, they have certain of the information of the x-intercept and the y-intercept. -4, 1 divided by 2, and also this will be 2. Okay, so that's there will be the intercept point here. Okay, so next step, find the vertical asymptotes, which we learned that the vertical asymptote could be found out from the zeros of these denominators, which you can simply know that the x equal to 1 and x equal to -2 will be the vertical asymptotes here. Okay, so when x equal to 1 and x equal to -2 will be the vertical asymptotes. Okay. And regarding to the horizontal asymptotes, okay, the horizontal asymptotes is defined from the degree of this numerator and the denominator, right? So since we learned the functions were shown here, so you can see that n is equal to 2 and m is equal to 2 as well. So they are the same of the degree. So we know that the horizontal asymptote of the sum of the degree in the numerator and the denominator, which that will equal to the an divided by the bn here, which that will equal to the an will equal to 2 and am will bm will equal to 1 here, which that will equal to the 2 divided by 1, which will equal to 2. Okay, so then the horizontal asymptote will be at the y equal to 2 here in this case. So you can see that will be from here. Okay, so that's the vertical asymptote, 2 of the vertical asymptote and the 1 of the horizontal asymptotes. Okay, so then just follow the graph of this function will be similar looks like this as we explained. Okay, but that also need to keep doing this further of the operations. Okay, which we could find the end behaviors of these for these regions. Okay, for example, the x equal to 1 and x equal to -2, and also that, and also when x approaching to this 1 divided by 2 and -4 here. Okay. Okay, so then we find the end behavior of these the functions, and then as we explain that when the x approaching to the certain of the term here. So since we have some of the information of this term, which 1 and the -1 divided by 2, and also the -2 and also -4, which they will have the intercept of this point, and also the vertical asymptotes of these 2 points here. So then we find the x approaching to these regions, and in this region, and this region, this region, and this region, and what happened of the function f of x. Then we could try to estimate the graph of these rational functions. Okay, so in the first of the case, if when x equal to 1, so we can find it when x approaching to the 1 kick here, which that will approaching to the left hand side of this of the function here. For example, we could using the x equal to 0.9 to estimate, to pretend that these the numbers at the left hand side of this 1 here, and then we could find the function f of the x, where the f of the 0.9 will equal to the 2 times of the 0.9 subject of 1, and x plus 2. Okay, so that's the original of the factoring of the function, right? So then we substituted 0.9 to the x here, which will equal to this term here, right? So you can simply you can do in some operation here, which that in the first term here will equal will be the positive, since that were 2 times of the 0.9, which is approximately equal to 1.8, right? So substitute the 1 will equal to 0.8 here. So that will be the positive sign here. And the same as the following term here, which will be the positive and the negative and the positive here. So you can understand that after we're doing these operations, the function will become to the negative here, which since that we'll only have the one of negative in this case. So we know that in these regions, at the left-hand side of this one of this function, so then this will be the negative. So you can imagine that this will be the negative sign. Okay. So in the case of the x approaching to the one at the right hand side here, so then you can use in the x equal to 1.1 to estimate the function of f of x at the right hand side of the one here, which you can see that the functions will also 0.1 to the x here. So then we will see that this sign will be all the positive here. So we can see that the x, this will be the x equal to 1 here. So you can see the function will be the positive at the right hand side here, and also the function will be the negative at the left hand side of this one, x equal to 1. Okay, so we can approximately understand the end behaviors of this the graph here. Okay. Okay, so this just these some example of the how we find the end behavior. So in this case, so in this function or in these questions, there are 4 points that need to be considered. Since we have the 2 of the vertical asymptote, right? Which the asymptote will be at this x equal to 1 and x equal to -2. So then we find the when the x approaching to these 4 regions, and what happened of these the functions. Okay, so you can see when the x approaching to the left hand side of the -2, and also approaching to the right hand side of the -2, and also when the x approaching to the left hand side of the 1 and right hand side of the 2. So you can see the sign of this y of x, the y function or f of x here, which you will see that they will be the negative infinite, and also the positive infinite and negative infinite, and the positive infinite in this case. And how we find it? So you can see that each of the term, we just find the behaviors of each of the term here, and then we find the final term, final behavior of these functions. Okay. So you can see in these regions, you can see that this will be the function x, and we have the end behavior, this asymptote at the -2 and asymptote at 1 here. So you can see that the functions in these regions will be the negative infinite. Okay, and the graph of these regions, this region will be the positive, and also by this region approaching it to this the 1 here, and this asymptote will be the negative, and also when the x approaching at the right hand side of the 1 here will be the positive here. So you can see the graph will be some kind of this term. Okay. Then next step, finding the horizontal asymptotes. Okay, so as we learn that will be the n degree of the n is larger than the degree of the m. No, the degree of the n is 2, and m is equal to 2. So you can see that n is equal to m, and then the horizontal asymptotes will equal to the an divided by am, or the bm, which will equal to 2 divided by 1. Okay, so then the horizontal asymptotes will equal to y equal to 2. Okay, so then also you can graph to find the some point here when find this from this table when x and f of x. When x equal, just find some of the basic point here, and then you could try into a scheduling of these functions. For example, that is the horizontal asymptotes at the y equal to 2, and these two are the vertical asymptotes. Vertical asymptotes, which that will be x equal to 1 and x equal to -2. Okay, and also they have the horizontal asymptotes, this point and this point here. With this point here, 1 divided by 2, and also this will be the -4. Okay, and also the horizontal intercept, y-intercept will be at this point here, where that is the y equal to 2. Okay. Okay, so that's the way we find to graph it out the rational functions. And also, if we find the domain and the range here, and since the domain was there from the x term here, which that x cannot be equal to 1 and x cannot equal to -2. Since when x equal to 1 and the -2, that will like this denominator become to 0 here. So the domain is any of the real number, but the x cannot be equal to 1 and the x cannot be equal to -2. And in the case of the horizontal, the range of this term, which they are related to the function of this, will be the result of this function here, which you can see there is no limited. All the real numbers in the could be satisfied with this function. Here, so the range is any of the real numbers. Okay, it's just the example of these rational functions and the graph of these rational functions. So we learned that the rational functions is the equal to the p of x and the r of x and the q of x, right? Then we could simply to sketch out the graph of these functions. Okay, so next section is the common factors of the numerator and the denominators. Since we know r of x equal to the p of x and divided by q of x, that will equal to the an xn plus of the an subject 1 times xn subject 1, and also plus to the a1 x plus of a0, and the denominators. So that is bn xn plus of bn subject 1 x subject n subject 1 here. Times of b1x and plus of b0 here. They also could do in the factoring, which that will equal to the x subject a1 times of x subject a2 to the x subject to an. Okay, and also times of x subject of b1, b2 to the x subject of bn here. Okay. So you can see that these the functions what we learn, although they all include the information of the function and also the operation with these polynomial functions, and now we learn some of the rational functions. And since we can factor in out of these the functions of the polynomial function both in the numerator and the denominators, so in some cases, we will find some of the common factors, which then if we find some of the common factor, we are usually doing some of the canceling. Okay, so we just cancel it of these functions. But when we cancel these functions, but from the original function, this is the factor of the original polynomial function in the numerator and also in denominators. Since we know the when the factors or when this x equal to when x equal to a1 and x equal to the b1, we know that this is the some definition of the rational function. So in the case we find some of the common factors and we cancel this factor, and we still need to remember that for example, in the x cannot be equal to b1 because they will also let this function become this will also let this denominator become to zeros in the case of the x equal to b1. So when we cancel these common factors, and then we just remember that in the domain of this x, they also need to remember that like this x cannot be equal to b1, for examples. And also that in the numerators, they will have some of the intercept. So you also need to know that when we define this, when we cancel these common factors of this polynomial function in numerators, okay. Okay, so okay, so that's the theme of this this section. Would like to express. So if we have this s of x equal to the p of x divided by q of x here, right? And if the p and the q have the do have the factors in common, okay, and then we may cancel. Usually we will cancel this factor, right? But only for those of the values of the x for which that the factor is not zeros, because we know that the divisions by the zeros is not defined, which that the denominator is the 0, right? So if we since we x is not defined at these values of x, and then when we graph of these rational functions, there will be holes at this point here. Okay. So we can we directly we give some practical example of these common factors with some common factors. For example, if we have the x rational function s of x equal to x subtracted 3 divided by x squared subtracted 3x here. From this term, you can see that in the denominators, they could be factoring out of the x, which that will be equal to x times of the x subtracted 3. Okay, so in this case, you can see that in the numerator and the denominator, they have the common factors of the x subtracted 3. So usually we will cancel off the x subtracted 3, and then it will result in the 1 divided by the x here, right? So you can see that the s of x that the s of x could be presented as x subtracted 3 divided by x squared subtracted 3x here, which that will equal to the 1 divided by x here. So from the graph, you can see that it's quite easy to understand the graph of this s of x will looks like this term, right? But I think from this graph, although you can find this term here, but the original of this function, they will combine with this x subtracted 3 divided by the x squared subtracted 3x here, which will equal to the x subtracted 3 divided by the x subtracted times of x subtracted 3 here. But in the case, you can see that when the x equal to 3, although the s of the x in this term 1 divided by x here. Okay, so we can simply write it down here. So I think you can simply use your hand to calculate, and then you will more understand the meaning of these common factors, which is s of x will equal to the x subtracted 3 divided by the x times of the x subtracted 3, right? So usually we will cancel all these factors, and then we will result in the 1 divided by x. But I think from the x, when the x equal to 3 here, so then s of the 3, so original then 1 divided by x 1 divided by 3. So that could easy to understand that cannot be that is satisfied with this function. Now, if you make this the cancel, if you include the cancel part here, which that will equal to 3 and x times of the x subject 3 here, which there will be 3 subject of 3, and also 3 times of the 3 subject of 3 here, which you can see this term will come to zeros here. So which is not satisfied with this function. Okay, so you can see when we define the functions or the rational functions with some common factors. So we just remember that they also the domain of this x also cannot be equal to the 3 in this case. Okay. Okay, so in the case of the two example, the correction 2 here, which t of x will equal to the x cubed substituted of 2x squared, and divided by the x substituted of the 2 here. So you can also find some of the factor in the numerators, which will equal to the x squared. Okay, and then we will left the x substituted of the 2. And also in the denominators, they will equal to x substituted 2 as well. So in this case, they will cancel of this common factor, right? Which they will equal to x squared here. So in this case, you can see if you still remember that the graph of these functions, which they will similar like this. And since the original rational functions was defined as this one, and in this case, the domain x cannot be equal to 2, since that will let this denominator become to 0, right? So in this case, the graph of these functions will be excluded of the 2 point here, okay, when x equal to 2. So in this region, so this will be the circles on this the graph here, which that means the graph they has the function of the graph, and but that included of this point here, and the same of this the s of x. So you can see from these functions, since that is the graph of this x here, right? S of x, and then that is the function when x cannot equal to 3. So you can find that when x equal to 3, so the function was not included of this point here. So we just need to understand the some common factors, or we do some common factors, and then we need to remember that the properties of these the common factors. Okay, so this is just a graph of this s of x. So you can imagine that although this the graph is quite simple, just similar like the x subfield 2, and also that could be equal to the x subfield 3 and x times of x subfield 3 here. Or we can imagine that that is x subfield 3 or x squared subfield 3x here. So from this graph, you can imagine that this graph could be using this graph to be presented. But remember that there is of common factors of the x subfield 3 here, which is not included of the x equal to 3 here. Okay. Or we can see that is the s of x is equal to the 1 substitute 1 divided by x for the x are not equal to 3. In the case of 2 as well, so the graph will be like the x squared. And then this will not include it when the x equal to 2. So you can see when the graph of this function. So this is the function, but not included of these 2 here. And also quite easy to make sense on this when the x equal to 2, and then it will let this f of x denominators become to 0, which not exist. Okay. Okay, so that's the some basic knowledge with these rational functions. Okay, so now we can take up 5 minutes break on this. Any questions on this rational the graph of the rational functions? Okay, so if not, we have about 10 minutes break from now. Okay, so and we will continue our next section on the 15 past 9. Yeah. Okay. So I'll see you later then. Hello, everyone. I'm coming back. So let's continue our lecture on next sections, which we will introduce you the slant asymptote and band behaviors of the rational functions. Okay, so I think in previous section we have understand the graph of these rational functions, right? Which that will related to the f of x equal to the 1 divided by x here, right? And then we could do in this certain of the stretching and shrinking, or the reflection, and also the sum of the operation with the of the graph from the 1 divided by x here, right? So, and I think from the this function here, we could find the sum of the vertical asymptotes, okay, and also with the horizontal asymptotes. And then the graph of this function will find some of the end behaviors of this function, okay. For example, in the case of this term, which when the x approaching to the infinite, and then or when the x approaching to the certain of the zeros, or the vertical asymptotes, and when the x approaching to the left-hand side of the asymptotes, and also when x approaching to a negative infinite, and see what the functional f of x represent. Okay, so that's the fundamental of the that's the some basic knowledge with this graph of the rational functions. Okay, so that's based on the vertical asymptotes, and also the and also horizontal asymptotes. Okay, but in some cases, as we explained, the functions they will have, in some cases we could see some of the graph of this function, as we explained, that they could be from the they are asymptote with these 2 of xx. For example, this is the vertical asymptotes, and also this is another type of the asymptotes, which that has not with this horizontal asymptote or the vertical asymptote, right? And also the functions of this the functions will have this certain phenomenon, which they will approach into this certain of the case, but there is no intercept of with this term here. But in the case of the vertical asymptote, which we quite easy to understand, that is from the denominator is not equal to 0, right? So that's from the if we find the vertical asymptote, that is from the zeros of the denominators. But in the case of this slant of in the case of this slant of asymptote, which they this not is from that is not from the vertical asymptote or the horizontal asymptote, but with this certain of asymptote. And also it's quite easier to understand the asymptote of this term here, which you can see that is the line with a certain of the angles. And if you still remember the some of the definition of the functions, this is belong to these linear functions. Okay, so that is the from the a or x plus b, if you still remember that, which they have certain of the slope, and also they have the certain of intercept with the b. Okay, so then this will, if the function will follow these they have the certain of the functions which they form the certain of the asymptotes which not intersect with this certain of function here. So that will from this will be defined as the slant of the asymptotes. Okay, we can simply say that this length of the asymptotes, which they have certain of the functions. Okay, instead of the vertical asymptotes x, instead of x equal vertical asymptotes, and also horizontal asymptotes, where the vertical asymptote could be defined x equal to somewhere, and horizontal asymptote is equal to y equal to some numbers here. But the length of the asymptotes will define as the ax plus b. Okay. So that's the theme of these sections. Okay. And also, after we find the asymptotes, and then we also determine the end behavior of these functions. Okay. And where can we find this length of the asymptotes? And as we define that is from the previous slide, we learned that this length asymptote was happened to these certain of this function, which they have the linear functions, which ax plus b here. And this happens when we have the sum of the vectors from the numerator and the denominators here. So if we have the rational function r of x equal to p of x divided by q of x, is the rational functions, and in which that the degree of the numerators is 1 more than the degree of the denominators, which means that when the n is larger than m here. Okay, and then we could use these divisions of the algorithms to express the functions in the form of the r of x equal to the ax plus b and plus of the r of x divided by q of x here. When this will from the degree of this polynomial, the numerators. This will be from the okay, maybe just to explain that in this the functions. This just from the maybe you can just go back from the original r of x equal to the p of x, right? Divided by the q of x, and so this will be from the in the both of the numerator and the denominators. They are the polynomial functions, right? And they have a certain of the degree of these functions. For example, there will be an xn to somewhere a0. Okay, there will be a bn bm x power of the m to the a b0, right? So they have certain of the degree. If you still remember, here's a certain of degree of m, and if you remember that when the degree of this n is the smaller than m, so we know that the degree of the numerators is less than the degree of the denominator. So then horizontal asymptotes could be found that is y equal to 0. When the n equal to m, then we know that the horizontal asymptotes will equal to the a n divided by b n. When the n larger than m here, which the degree of the numerator is larger than degree of the denominators, then there's no horizontal asymptotes. But in this case, since the degree of this numerator is larger than m, so in the case you can see that when the 2x squared and divided by the plus 2x, okay, and then in the denominators, they have the degree of this term, and for example, subject 2. Okay, in this case, you can see the denominators of the degree of the numerator is 2, and the degree of the denominator is 1 here, which is larger than which the degree of the numerator is larger than the degree of the numerator. So in this case, you can see that you can also do in the further of the divisions, which that will from the certain of the degrees plus of the sum of the remainders. Okay. So in this case, you can see you can simply doing this the divisions, and then they will have certain term here. So you can see that they will certain term plus of the sum of the remainders and divide by this original of the x subject to. I have no space on this one, so maybe you can find some other space. So in the case x 2x squared. Okay, anyway, so that's a plus of 2x. Okay, maybe plus of 4x here. Okay, and then this when the denominator to x up to 2 here. So in this case, you can try to use this 2x squared plus of 4x and divide by the x substitute 2. Maybe it's better to find this one plus 1 here, plus 1 here. Okay. Then we know that this will be the quotient will be the 2x, and then 2x squared subtracted of the 4x, which is the minus, this will be the ax plus 1. Okay, so then we know that with the plus of a, which will equal to the ax subtracted of the 16. Because I thought this one, because you see that these are 2. This will be 8. Okay. So then this will equal to the minus 15. Okay. So the function could be presented that the equal to the qx plus of a. Okay. And the plus of the minus 15 divided by x substitute 2 here. Okay, in this case. So we can see they have these functions, and they have the functions, the origin of these functions. Then after we're doing the division, so then they will equal to 2x plus a, and the plus of the minus 15 divided by the x substitute of 2 here. And also in previous learning in the polynomial functions, we know they could using the certain of the division theorems to find the quotients and also find the remainders of this function here, which in this case they have the remainder of the minus 15, which the degree of the numerator is less than the denominators in this case, but they also have the certain of this function, or this certain of the terms in the previous, which they will apply this division algorithms of these rational functions. Right? So in this case, we call this one is the number of the irreducible of these the functions. Okay. So then, as we learn this one, the rational function could be also find this this form, which that when we meet this polynomial, the degree of the polynomial function in the numerator is larger than the degree of the denominators here. Okay, so since we have this some of the knowledge on this the rational function here, so the degree of the R in this case, after we doing these divisions, the degrees of the R, or we call that is remainders functions, is the less than the degree of the Q, and where the A is not equal to 0 as the original definitions, and this means that as the x approaching to the positive or negative infinite, the R of x divided by Q of x will approaching to the 0 here. So the larger value of the x, the graph of the y equal to R of x will approach to the graph of the line to the y equal to the ax plus b here. Okay. And in this situation, we say this y equal to the ax plus b is the length of asymptotes, And also we call that is the oblique of the asymptotes in this case. So this is just what we explained that when we meet this the P of X is the degree of the P of X and is larger than the degree of the Q of X, and then we could do in these the divisions theorems, right? It could be this is from the long divisions and theorem, and also you can use in some of the synthetic divisions. It depends on how you're familiar with these divisions operation with the polynomial functions. And once we're doing this long divisions here, and then we will form they will form this certain of the 2x plus a and plus of the minus 15 divided by the x sub 2 here, which they will have the this function. When we find the end behavior of this function, so since that is the degree of this r is smaller than degree of the denominators part here. So you can see the function will approaching, and they will form define that the ax or the 2x plus a is the slant of the asymptotes, and the when x approaching to the minus 2, for example, you can see when the x approaching to the 2 here, they will have the vertical asymptotes x, y, and this is 2. So in this case, when x approaching, they have their vertical asymptote when x equal to 2. And also they have the length of asymptote when 2x plus a here, which that will be the slope is 2 here, which they will be similar. And the intercept of the y when x is equal to 0. So they will from here. So for example, that is the a, 0 and the a here, okay? So the line will be this term here. So after we find these two of the asymptotes, right? This is the vertical asymptotes. And this term, 2x plus a is the length of the asymptote here, right? And then you can determine that the x approaching to the infinite and also the negatively infinite, what functions of the f of x will happen. For example, it may be from here and from here, okay? So the graph will be looks like these figures and approaching to these two with these two of the asymptotes here. Okay, so that's called the slant asymptote, and also call that the oblique of the asymptote here. Okay, so here we give example of this function r of x equal to the x squared subject of 4x subject of 5, and divide by x subject of 3 in the denominators. So first step is the factoring, which the numerator will become to the x plus 1 times of x subject of 5, and in denominators will equal to the x subject of 5, x subject of 3 here. Okay, and then find the x intercept, which the x intercept will like this, so y equal to 0, or when the y equal to 0, which that will be the numerators will be equal to zeros. Okay, which that will equal to the 0, this will equal to 0. So then x equal to the minus 1 and the x equal to 5 will be the x intercept, okay, in these two. When the y to find the y intercept, we like this x equal to 0, right? So then the y of the zeros will equal to this term here, which will equal to the 5 divided by 3, okay? So then the y intercept will be at the 5 divided by 3. And then find the vertical asymptotes. We simply know that is from the denominator, to find the zeros of the denominator where the x equal to 3. Okay, so in front next find the end behaviors. of these vertical asymptotes. For example, when the x approaching to the left-hand side of this 3, and then y will approaching to the infinite. When the x approaching to the positive of 3 here, and then y will approaching to the negative infinite here. So the horizontal asymptote here, since we know the n is larger than m, so there is no of the horizontal asymptote, right? And then we find the slant of the asymptote. Since we know the degree of the numerators is the one more than the degree of the denominators, and then the functions has the slant of the asymptotes, which we after we don't doing the divisions of these functions, which we know that is the divisions. For example, using the syntactic division 1, -4, and -5. And then this will be x subject 3 here, which we are using the 3 here. If you still remember some operation in the polynomial functions, which that will be 3, and that will be -1. And also times of the -1 here, it should be -3. And then you're doing this some summations which will equal to -8. Okay, so you can see that here is quotient, here is the remainders here. So in this function could be represented into the x subtracted 1 and the subtracted of a divided by the x subtracted of 3 here. Okay, so this is the way of doing this synthetic of divisions. Okay, so then they will form this term, right? As we are shown here. So then as we find that since the degree of the n is larger than m here, and then there is the slant of the asymptotes, where the slant of asymptotes will be this term. Okay, so here we y equal to the x subtracted 1 is the slant of asymptote as defined. Then when we are sketching out of the rational functions, well, since we know we have the vertical asymptotes where the x equal to 3, okay, and also we have the slant of the asymptote where the y equal to the x subtracted of the 1 here, okay. And also we find the anti-behavior when the x approaching to the infinite, the function will approaching to the when the x approaching to the infinite, so the y will approaching to the function will approaching to the infinite as well, positive infinite. When the x approaching to the 3 here, so the y will, the function will, f of x will approaching to the negative infinite here, which will approaching to these directions. Or when with the x approaching to the this part here, the function will approaching to this positive infinite. Okay, so when the x approaching to the negative infinite, so the function will approaching to the negative infinite as well. So you can see the part of this graph will be looks like this two term here. Okay, that's the way we find this. This some of the example. If we mean that when the degree of the n is larger than n, then we know that to find the slant of the asymptotes. And then the other step for the graph of this rational function, just follow the origin of the graph of the rational functions. Okay. Okay, so this is just the two of the part of the rational functions. Okay, so here we are also we know that the in some of the physics and also some real situations that they have many applications they have certain models with the rational functions. Okay, so or you can say that the rational functions equal to the polynomial functions divided by the cube of our function, and both of these numerator and the denominator, they are the polynomial functions. So in many of the physics, they could using this rational function to present a certain of these physics phenomenon or the models, and then you can find the solutions or find the graph of these the functions to present a certain of physics phenomena. Okay. So here we give some applications which they are using the rational functions. And also the rational functions occurs frequently in scientific applications of the algebra. For example, in the electrical resistance, for example, and when these two resistor with this resistance of the R1 and the R2 are connected in parallels, and their combined the resistance of R is given of their formulas R equal to the R1 times of R2 and divided by the R1 plus R2. Because I think that's related to the some of the integrated circuit design. I'm not sure if you learn some of the IC design or integrated circuit, which we know some electronic devices or in some electronic component, they contain of the current, and also the voltage, and also the resistance or some capacitors. These four are the common of the semiconductor devices in component here. Or for example, if you have the cell phone, so you can know that why the cell phone could be worked like can be worked with such or some of the tiny of the IC devices here. Or you can see why the computer can work because they have some of the central process unit, which that is combined with this many of the current control, voltage controls, and also resistance control and the capacitor control to control the on and off of the electronics device, and to do the further of the calculations with the central unit, central process unit, right? And each of these current I is using like Q, and V present that the voltage, and R is represent the resistance, and C means that capacitor. Okay, so we can imagine that the current means that the amount of this electronics flow, okay, and the voltage is the amount of this electronic the numbers of the voltage or the numbers of the current, okay, and the resistance means that the devices that have the ability to how many of the electronics will transmit or transport from this certain of the materials or certain of the electronic devices, okay, and the capacitors means that the contents of these electronics, okay, the amount of the contents of these electronics, and as we explained that these four devices could control the calculations or could control the electronic devices. This could control the how to calculate the mathematics. Maybe we can use in some of the simple way to explain of this the properties of these four devices. But anyway, so that's how the IC design, or the IC means that the integrated. If you know that IC, or now I think the many of these components, like the computers or like the cell phones, there are many of the IC inside of this cell phone, and each of the IC they just help the electronics device electrons transport in the certain of the IC to calculate or to operate the certain of the functions of the cell phone, for example. So inside of this IC or integrated integrated circuits. Okay, so it just means that here is the IC. So there are many of the I, B, R, C component to combine together to doing the computer calculations. Okay, just simply to do that. So you can see that the IC is quite important in the semiconductor industry. Okay, but anyway, here we just give some of example with the resistance. For example, if we assuming that the resistance, there are two resistance which they could have a different of the abilities, different of the resistance. Okay, they have they have different of the ability to transport the electrons. Okay, for example, we know that electrons passing through this resistance. So if the resistance is very large, okay, so then if we give the speed of the electron transport, maybe originally that they will transport with a certain of the speed, okay, it's very fast. But after we passing through this one, maybe you can see that there are maybe two of the or three of the electron unit passing of the resistance, okay, the resistance. So maybe the some part they will miss it as after passing through this resistance. For example, it will only have the two of the electron passing through this term here. Okay. So and this is the ability to control the amount of the electron transmit into these certain devices, right? So with this term, so you can know how you can control the amount of this electron transmit. Okay, but maybe there are many details on this part here. If you are interested, maybe you can discuss in the later if you are interested. Okay, but in the case of the resistance, so they could be a continuum of the connection with the two different of the resistance, for example R1 and R2. So the R will equal to the R1 plus R2. Okay, so that's from the continuum of the connection of this resistance. But in the case of the connection with the parallels, for example, there are two of the resistance connected parallel, right? Where this R1, here's the R2. So then the total of the total of the resistance of these devices, okay, so will equal to the R1 times of R2 divided by the R1 plus of R2 here, okay. So this is quite easy to make sense on the total of the resistance here. So it depends on how you connect of this resistance. So in the case of the connection parallelis of this resistance, so the functions, they will form the functions are equal to the R1 times of R2 divided by the R1 plus R2 here. Okay, so you can see that the functions, well, they will form this function here. Okay, so now since we understand the sum of the models of the parallel connection of the resistance, so here we suppose that the fixed of the ohms resistors is connected in parallel with the variable resistance as shown here, which that means the resistance, the total resistance is equal to the 8 ohms. Okay, so they will combine with these the two of the connectors, the resistance. Okay, so then the fix of the ohm resistor is connected. Okay, so this is not the total. So this is fixed of the 8 ohms of the resistor is connected in the parallels with this variable resistance here, which that is R1 is equal to 8 and R2 is equal to X, which is unknown variables here. Okay, so then we will know that the A times of the X divided by the A plus of the X here. So that's the total of this resistance. Okay. Okay, so the question is if the resistance of the variable resistors is denoted by the X here, then the combined resistance or the total resistance is the function of the X. Then graph of the R and given the physical interpretation of this graph here. Okay, so we define the R1 is equal to A and R2 is equal to X into these formulas, and then we give the function R of X equal to the AX divided by the A plus of X here. And since the resistance cannot be negative here, so we know that this will be larger than zeros. And this functions has the physics meanings only when the X is larger than zeros here. Okay. So you can see that's defined also the range. We know the range of these functions. Or we can see that y, where y is larger than 0 here. Okay. Okay, so that's some of the information we get it from these models and also from the description of this basic phenomenon. And we will result in this the functions, right? Okay, then we could. Yes.
I got a question. Where can I find more information about this topic and electrical resistance on that?
Okay, so you can find some, I think, basic of the electronics textbooks. I think there are many of the informations on that. Okay, we can simply type this a 电工学. Okay, some electronics. I think we have some of the course. They will lecture you some of electronics. Some physics, yes. I think just some ELECTRC. Or you can Google some of the technical work of the electronics, or some of the resistance, and also some of the integrated circuit. Okay, some of the circuits, CUIT, yeah. So I think there are many information on that, but you know, it's just some of the basic of the physics with the resistance. If you connect with the parallels, okay. But if you connect with this continuous connection, so they just simply using the R1 plus R2. But as we know that in the IC, in the integrated circuits, there are many of the, with the small timing of the devices, there are many of the link to control the transmission of the electronics, which that will control the switch on and off. Okay, if the connection of these two link was connected, and then the electron will pass into these devices, right? So then you know that these will be defined as the on. So then you can, I think the device will work. If if these devices is not connected, and then this will be the function will equal to 0. But if that is the connected, So then this will equal to 1. So then this will just combine with this 1. The code of this one will be 0, 1, 0, 1, or 1, 1, 1, something like that. Yeah. But you know that the later these are related many of the calculation, because you know that this will be from the 1, 2, 3, 4, 5, 6, 8 digit. You know, A, D, I, G. 8 digits. They could be from the they have many of the variations, since you know they could be the 1 and the 0, and this also could be 1 and 0. This is 1 and 0, right? So you can see each of these mathematics will be 2, and also two options. But later, I think that's from the some of the exponentials in chapter 4. Later we will explain that this part here. But you just know that in some of electronic devices, they are using certain of the control to control the on and off. Okay, and and at the moment, maybe the basic computer, they have 8 digit, but nowadays I think they are more than of the 8 digit already. So they contain many of the applications of that. Okay, but I think that you can find some basic knowledge from this. You can start to Google some of the basic technical word, and then they can give some basic explanation on this integrated circuit. Yeah. Okay.
Thank you, Professor.
Okay, no problem. But that's very interesting thing, because you know, in the resistance, because a lot of story on this one, it's very interesting, because you know some of the, if you're using the resistance, or you can see the traditional light bulb, if you still remember the light bulb. Okay, and let me draw it. And why the traditional light bulbs, they will have the they have the light, right? Because you can see the electron passing through the certain of the resistance. Okay, so then and the electron will pass into the certain of materials, which this material, they have certain of the resistance. Okay, the resistance means that when the electron pass into this electron or these materials, they will moving slowly from this point to this end here, right? So then some part of the energies will using the light or the heat to emit. Okay, so they will transmit the electron to the light. Okay, so you can see the light bulb will have the energy, or like, for example, they have the light, and they have the heat, for example. Okay, with a certain of the resistance. But in some case, some of the wood or some plastic, so there's no of the electron very difficult to moving from the plastic or from the other of the wood material, for example, which they have the higher of the larger of the resistance here. Okay. Which that quite difficult for the electron to transfer from the wood or from the plastic here. So in that case, the R is very large. Okay. So already can see that in the materials, so they have the metals, and also for the wood. Okay, so the resistance of the wood is very large than the resistance of the metals. That's some of the basic knowledge of that. But later we can learn some of the properties of the materials, and then you know that what's the difference of the resistance. But I think that's interesting, that since you can know that we control the difference of the resistance, and then we can control the on end of the electronic devices here. Okay, but I think the way to control that is far more faster than the electronic devices here. Okay, but anyway, it just shows you that in the electronic devices, they have or you can see that the rational function we could apply this certain of the rational models with the sum of the electronic devices or in the resistant devices here. Okay, it just gives some of the basic definitions. This some of the examples of the rational function. Okay, so I think that's from this example. So we can form these models, which ax divided by the a plus of x here. So we can see the r of x. Could be that's p of x, and divide q of x here. But p of x is ax here, and q of x is a plus of x here. Okay, so we can see these are belong to the both of the polynomial functions, and then from these rational functions, and then you can do in this further operation and to sketch out this the function. Okay, for example, in the beginning you can sketch out this function since this r of x is larger than 0, right? So they only exist in the positive part of this term. Okay, so then we will sketch out these set of functions. But if you enlarge, so you can see the trend of this the resistance, which is r of x. Okay, so this is so if you enlarge this the range between the 0 and the 20 here, and the vertical the view of this the function here is 0 and the 10 here. But if you extend the horizontal term here to the 0 to 100 here, and then you can see the graph. You can use in this the graph to explain that the phenomenon of this resistance. For example, it will start from the beginning. The resistance will increases, but as after certain of this term, for example, the you can see that will be equal to 8 ohms here. So we can see in the beginning of this time, for example, and then the electron will increasing or transmit through this draw it better. Okay, so you can see that if you know that the ohm here is 8 ohm here, so here is the x ohm here. So you can see in the beginning of these functions, they will start to they will start to transmit electrons will passing through this resistance, right? Maybe you can this is resistance. So the electron will passing through this resistance, okay, from this parallel connected, and then they will also transmit into this part here, okay. But in some case, they will have certain speed, maybe 2 of the electronics. They only have one of the electronic devices will pass into this one, and it depends on the materials or design of this resistance, right? But this also shows you that in the beginning of the electronics, they will pass into this resistance, but with the certain of the time, and then they will or the amount of this resistance, they will only limited to this 8, for examples. You can see the it just shows you the resistance of this term. They have certain of content. For example, they could pass into this certain of the electronics inside here, okay, and they also have certain of electronic devices, electronic transmitted in this part here, okay. But I think that they have the limitation because maybe these in this case, so they will have full up of this resistance inside of this resistance, okay, which they may have another limit. They have reached to the limited of this resistance already. So you can see the phenomenon of this resistance will have limitations, which they will slow down of the electronic device, electron transmitted in this resistance, okay. So this is how we are translated from this graph here. If they have the certain of these rational of the models, a or x divided by the a plus of the x here, okay. So the combined of the resistance R increases as the variable resistance increases, right? And if we widen of the viewing of the rectangular to the 0 and the hundreds and by the 0 and the 10, and then we obtain the graph of this function here, right? So if we are increasing that the x here, and they will not limit, they have limited to the 8 here, so they will not over the 8 ohms in this combine of this resistance here. Okay, so for the translation from the graph here as we shown, for larger of the x that combine the resistance of R, the level of, and then we're getting the closer and the closer to the horizontal asymptote of the R equal to A. And no matter how the large of the variable resistance of X, and the combined resistance is never greater than the 8 ohms here. So from this graph, we can see that you can see the trend of these electronics devices with this combined of the resistance. Okay. So I think from the beginning, so you can see that if you know that the model of this resistance, okay, and then you can predict or you can design the resistance needed by the combining of these two resistance. Okay, so that's the way they are doing this the IC design. But as we explained that this is belongs to the resistance, but in the integrated circuit here, they include the current and also with the voltage and also with the resistance, right? And also with some capacitors. So inside here, you just doing, in some of the electronic devices, you may include it, for example, in the resistance, and also they will doing this certain of the IC design, and also with some of these the capacitors, okay, and then to combine some of them, they will they will doing these parallel connections, or they will doing this the continuous link, okay, to control the on and off of the certain of the IC. Okay. So inside of this one devices, you can using this one to explain the phenomenon of the electronics. But in detail, so they may not conclude. They may combine with this maybe thousands of the resistance capacitors and also the voltage controllers and integrated circuit in the integrated circuit here. Okay. Okay, so that's the some of the example of the rational functions here. Okay. So any questions? Any other questions? If not, maybe we can do another of the 10 minutes break, okay? So, and now it's already 8:09, 8:10. So we will continue. I will be back. We will be back to continue next section. 18:10. Okay. So I will see you later. So take a break.
Okay, Professor.
See you later. Okay, hello everyone. I'm coming back. So let's continue next section. Okay, so next section we'll introduce the some equalities in the polynomial function and the rational functions. And I think that in chapter 2 we have learned some of the inequality, right? So normally when we see the function f of x, if we would like to find the solution of the function, so usually like that is equal to 0, right? But in some case, in some condition, or in some physics, or some real situations, the functions could only apply at the function large or equal to large or equal to, or smaller or equal to, with a certain of the numbers, for example, large or equal to 0, and also with some other of the functions. Okay, maybe for example like q of x functions, or some of the different kind of the function here, which that define in some physics models define that this function can only apply in the certain of the condition, right? So these are some of the basic knowledge with these functions inequality. And also when we meet this polynomial function and the rational function, we will meet some of the equality as well, which the functions will also form these 4 symbols, which they were larger or larger than equal, or smaller and equals of this certain of the zeros, and also the polynomial functions here, okay, or some other rational function, okay. So with the different of the functions equality, they will have different of the operation as well. For example, in the polynomial function and also in the rational functions. Okay. So in the polynomial inequality here, and I think that's quite makes sense or easy to understand that the polynomial inequalities, since we know the p of x equal to the an xn plus of the an subject 1 xn subject 1 and plus of some number a1 x plus a zeros, and also could factoring out of this x subject a1 x subject a2 etc. here, right? Which usually in the previous we know the polynomial function could be that equal to zeros, and then to find the solutions of this function. And in the equality here, so we know that this will form with these symbols of the larger or equal and smaller or equal than certain of form here, right? Then we could do in this the same certain operations. For example, the combine of these two functions, or to evaluate it with these inequalities with some basic of the polynomial operation. Okay, so this just shows you the important consequence of the intermediate values theorems, that the value of the polynomial function p do not change in the sign between the successive zeros. And in other words, the value of the p between the successive zeros are either all the positive or the negative here. And this just also just shows you the graph from the graph here. So original, we know that previously we know the functions. Okay, so with the polynomial function, they could be from different kind of the features of the figures on the xy coordinate plane, right? So since we know the functions, this is the functions, and we know define the domain, and also we define the range of this term. So in the term of the range here, it also depends on the definition of the p, the y, right, or define of the p of x here. And in some case, the functions only exist at the when p of x is larger than 0. So then we know that the graph will be shown in these regions, okay, or in these regions, and also in the regions, in these regions. And others, for example, in this part here, which that belong to the y equal to 0, or in these regions is the y equal to 0, less than 0, or the p of x is less than 0 here, which not belongs to this the definition of the equality when the p of x is larger than 0 here. So this just shows you how we define the inequality in the in equality of the polynomial functions. Okay, so from this graph we can easily to understand that when they have this inequality when the p of x larger than 0 or equal to 0, smaller than 0 or smaller than equal to 0 here. Okay, so in the case of the p of x, they could be also larger than q of x and larger or equal to q of x, or smaller than q of x, or smaller than or equal to q of x here, right? In the case, if we have the polynomial functions, okay, so for example, it's like this term here, okay, and then the q of x, if that is the p of x, and if we define that the q of x here, so maybe I will say that maybe you'll find, if we find that p of x is equal to the for example, is x squared here, p of x. P of x equal to the x squared here, right? Or maybe you just simply rewrite it again because we need some space to. We assuming that we have the p of x p of x function is the x squared, for example, okay? And then if we have another function, which that p of x and the q of x, which they have certain function, right? Here's the q of x. So in the polynomial inequality, in some case, if we would like to find the p of x, since we know that if that is larger than 0, okay, larger or equal to 0, so then the graph of these functions will be this term, included this term here, right? So we can use in this function to present these functions. But in the case of the p of x larger or equal to q of x, okay? So then the graph of these functions, then we could simply know that that will be the regions, okay? And also with these regions, and also in these regions, okay? Since we know that this is inequalities, okay, so then we know that this will, since that will be equal to this region here, because you know that this only, the function is only satisfied with this p of x or larger than or equal to g of x here. So since we know the p of x was all these. Okay, original, this is the p of x, right? So in these regions, we have this one is p of x, and this one is q of x here, right? So if you are looking for this polynomial inequality when the p of x larger or equal to q of x here, so this was a discuss of this region here, which in these regions, okay, as we shown here, okay. Or in further to doing the operation q of x, substituting both sides, we just substituted q of x here, okay, q of x here, which is larger or equal to 0. So after we are doing this the region operation, so we know that in this only in this region we are satisfied with this the definition of these polynomial inequalities. Okay, this just shows you how we are using these polynomial inequalities. Okay. So in polynomial inequalities, we here just some example. If we have the polynomial functions equal to the 4x substituted 4 times of x substituted 2 times of the x plus 1 and times of x substituted 0.5 and times of the x plus 2 here. So from the polynomial function, we know that they will have the x-intercept at the x equals to 2. They have the zeros of this point here, which -1 and 0.5 and also -2. Okay, in this case, so you can see they have the zeros at this 4 point here, where this one is 2, 4, 5. So assuming that there will be the this one, so this will be 2. This will be 1 divided by 2, and this one will be -1. Okay, so this will be the -2. So you can see they will have the zeros, and then we are finding the graph. We are using the any behavior to find the graph will similar like this term, right? And then if we have this polynomial function where the p of x is larger or equal to 0, and then we just find these regions. Okay, these regions when the p of x larger or equal to 0. But in this region, if you are looking for the when the p of the x smaller or equal to 0, so then you could find the regions between the below of this y x-axis here. Okay. Here shows you some the steps for solving the polynomial inequalities. So first step is moving all the terms to the one side. And this is quite makes sense on the polynomial function, right? So in some case, as we know, the p of x will larger or equal to the q of x in the case of these inequalities. So just simply both sides we are subtracted of the q of x, okay? And then the right hand side will become to a 0, okay? And then you can do in this further of the evaluation of these polynomial functions, okay? And then we are factoring out of these polynomial functions, and then find the real zeros of this polynomial function. And then since we find the zeros of this polynomial function, right? For example, and then we will find the intervals, which we can define this 4 interval, 5 interval, depends on how many of the zeros you find them in that polynomial function. And then we find this region and define the functions. F of x is the positive or negative part here in this interval, right? And then we can make a table or the diagrams and to define each of them and find the final of the f of functions is the positive or is larger or equal to 0 or less than or equal to 0 in this term. And then we solve these polynomial inequalities. Okay. So here we give examples of the polynomial inequalities on the 2x cubed plus x squared plus 6, which is larger than 13x here. So here's the p of x, and here's the q of x here. Okay. So here the degree is 3, and then here the degree is 1 here. So then the first step is move all the terms to the one side here. So we move the right hand side to the left hand side here. So both sides we are just substituted of the 13x here, which will result in the 2x cubed plus of the x squared substituted 13x and plus 6, which is larger or equal to 0 here in this term. And then the left hand side of these polynomial functions will form this form, right? Then the step 2, we just factoring out of these polynomial functions. which we basically find the x substitute 2 times of 2x substitute 1 and times of the x plus of 3 at the left hand side here, okay? And then which that is the larger or equal to 0. And then the zeros of these polynomial functions will equal to the, here will be 2, and here will be the 1 divided by 2, and here will be the minus 3. Okay, so here we found these 3 of the zeros of these polynomial functions, right? And since we find these 3 polynomial functions, we can just simply draw this the point, which is 2 and 1 divided by 2, and here is minus 3. So in this case, you can find the functions will have the this 4 of the term here, which this interval, and this one here, okay? So you just define that in the polynomial function, there could be the positive in this positive or negative in these 4 regions, right? So you can find the intervals will be these 4, which so that is the positive infinite and the negative infinite at the right and the left of the end. Okay. Then we make a table since we find this 4 interval, right? So we will see what happens or what's the graph or what's the phenomenon of these the functions in these 4 intervals. So in the case of the x substituting of 0, substituting 2, the regions at the left hand side of this negative 3 here will be a negative. So you can simply using the negative 3. Then this will be maybe you can negative 4 here, okay? In this case, so you can see that this function will be equal to negative. And then in the interval between the minus 3 and 1 divided by 2, there will be the negative. And this will be also negative here. But when the x is larger than 2 here, then there will be the positive here. Okay. So this is quite easy to make sense on the phenomenon of this function, right? And also the other 4 of the zeros, so you can also do in this same of these estimations and see that what's the result of these functions in between these 4 regions. And the last row that just shows you the function, which is x substitute 2 times of the 2x substitute 1 and times of the x plus of 3, which that is the function of the p of x, right? The p of x, right? So then you can see that in this region 1, so I think all these terms are the negative here. So then you will see that the term of these total functions will be the negative here. And also in the interval of these 2, minus 3 and 1 divided by 2 here, they also have the same of this. And in this region, so this sign will be the negative times of negative. So this will be the positive. So the positive times of the positive here will be the positive as well. Okay. So in this region is the positive. And also in the case of the x larger than 2 here, so this region, the sign of this function is also the positive here. Okay. So then if we are looking for the functions, which function is larger or equal to 0 here. So only with these 2 regions are satisfied with this equality here. So you can see the solution of this equality will be the interval between the minus 3 and the 1 divided by 2, and the interval between the 2 and the infinite here. Okay, so that's the way we find these inequalities. And if we sketch out of this function here, so you can see we find these intervals. This will be 2, and this will be 1 divided by 2. This will be the minus 3. Okay, so they have intervals, and we have find the end behaviors, which that function will be the. If you still remember the functions, is the Okay, so if you review back of these functions, okay, the p of x is equal to the 2x cubed, and plus of the x squared substitute 13 of the x, and the plus of 6 here, which is larger or equal to 0. Just make sure that is correct. Okay, so that's the correct. So you can see that this will be the 对 here. According to the end behavior definition of the polynomial function. So you know that this is the art of these functions and also the positive term here. So you can see that will start from here, right? And then you can know that you can using this graph, or you can using the definition, which that they have a degree of the 对, so they will have the two terms of this term, or you can find out two of the local maximum and local minimum of this function, right? So you can using start from here, and then you can pass into these the zeros of these polynomial functions, and then you can find the phenomena between these two, and then you can drawing this out of this figure here. This is what we learned in chapter 2 and chapter 3, right? So after we figure out this function, and then if we are looking for the p of x larger than 0, so then we just define that the function, this region p of x is larger or equal to 0. If you are looking for the function p of x is smaller or equal to 0, so then you will define that in these regions. But it depends on you. So that depends on how you define this function. Okay, so that's the example of these polynomial inequalities. Okay. Next is the rational inequalities. This also the quite fundamentals, and also I think the inequality method just the define of the inequalities just as we are defining in the functions, the inequalities. But in rational inequality here, just unlike the polynomial functions, since we know it just shows you in the polynomial function. Polynomial functions, okay. So the function, we know that could be any of the graph. Okay. Okay, so but in the rational function, okay, so if you know that the rational function graph will be something like this 10. Okay. So you can see that in the polynomial functions, the graph of this polynomial function usually that is continuous. Okay. So then you can find some of the zeros. Okay. But in the rational functions, and then you know some part that they will not continue, which they will have the vertical asymptote, and also with the horizontal asymptote, and also the stand of the asymptote, and depends on how you define the rational functions. But in the rational inequalities, which they will also have the certain of the r of x equal to the p of x. P of x divided by the Q of x, right? Which is larger or equal to zeros. And then you can also using they have certain of the equalities at this point here. And then we will just find some of the operation with this P of x divided by the Q of x first. And also just find the some of the factors, the same as the normal step of the equality, like factoring out of the rational functions, right? And then we find the intervals, or the zeros, or the intercept, or the zeros. Okay, or of the numerators and the denominators. Okay, and also find the vertical asymptotes and the horizontal asymptotes, or even with this slant of the asymptotes, right? And then we also find the intervals. Okay, and also we can using these tables to find each of the term. Okay, each of these terms here, which they are the positive or negative, and then find out to find the last the function p of x, or we can say that r of x. where that is the positive or negative here, and then to define that the rational function inequality here. So I think that's quite similar to this the polynomial function polynomial inequality as well here. Okay, but in the rational inequality, they have the sum of the discontinuous part, which that is the vertical asymptote. Okay, so the vertical asymptotes that of the rational functions is the breakup of the graph into the separate of the branch here, which we see that they will be from these two graph here. So one is the right hand side, one is the left hand side, and the function one is the positive, one is the negative here. Okay. So the interval on which the r does not changes the sign are determined by the vertical asymptote as well as the zeros of the r. And this the reason for the following definition, that if the f of r of x equal to the p of x divided by q of x is the rational functions, and the cut point will be at these vertical asymptotes, where the will be the cut point of the r are the value of the x at the which either p of x equal to 0 or the r of x equal to 0 here. Okay, so this quite makes sense on the r of x equal to the certain numbers. Okay, divided by the certain numbers. Okay. Okay. So in other words, the cut point of the r are the zeros of the numerators and the zeros of the denominators, as we see. Here is the example of the rational functions originally, right? Which they are x sub 2 and divided by the x sub 4 plus of the times of x sub plus of the x plus 3 here. Okay, so in this case, we can see the vertical asymptote will be x at the equal to 4 and x equal to minus 3. So you can see the vertical asymptote. And also the horizontal, the vertical asymptotes. And also the horizontal asymptotes, you can see that when it's equal to zeros here. So, and also this n is smaller than m here. So you can see the horizontal asymptote with y equal to 0 in this case, okay. And also with the intercept here, which that will also intercept with this x equal to 2. Okay, so you can see the function will equal to 2. So the domain of this term will x not equal to 4 and also not equal to minus 3. Okay, and the range of this term here will any of the real numbers here. Okay, so that's when this meet these functions is the equal to the this function, right? But when we meet this r of x is larger or equal to 0. So in this case, you can see when r of x was resulting from the any of the x number of the function, right? So in this case, you can see that the r of x is larger or equal to 0. So in these regions, which that will be the negative, which that will means that r of x is less than or equal to 0 in this case. Right, depends on how you would like to find the rational inequalities. Okay. Here are also some steps for the to find the rational inequality, like the move all the terms to the one side, and also the factoring out the numerator and the denominators, and to find some cut point. Okay, and then find the intervals, and make the tables or the diagrams, and also solve this function. It's quite similar to this some function equality. Okay, so here also we're doing some of the equalities of the rational functions. Okay, so the following is the procedures, like the we move all the terms into the one side. We move this one to the left hand side here, which will be the subtracted of 1 here. And then and then we are not doing the further of the evaluations. Sorry. Okay, so then we are just doing the further of the evaluations, and then we're just using the same of the denominators, right? So the 1 could be represented into the x squared subtracted 2x subtracted 3, and also in the numerators also could present that one x squared subtracted 2x subtracted 3 here. Okay, so then we can using the same of the denominators, and then the numerators will be this original function subtracted of this function, this denominator, right? Okay, so we are using and combine these common denominators and then doing the further evaluation, which will result in the 4 substituted of the x squared in the numerators. Okay. Then the left-hand side of the inequalities is the rational functions, okay, which will result in the 4 substituted of x squared divided by the 2x squared substituted 2x substituted 3, which is larger or equal to 0. Okay. Then we are factoring out of the numerator and the denominators here, which the numerators will become to the 2, which that will be a 2 squared, right? Which will 2 plus of x times of the 2 substitute of x here. And then in denominators will be 1, 1, and 1, 3. That will be negative, so we are using this 3. So then it will be x plus 1 and also x substitute of 3, okay, in the denominators. Okay, so then we could find the sum of the cutting point here, which that will equal to the x will equal to the plus 2 and minus 2, and also will be the plus 3 and minus 1. Okay, so these are the point of the intervals. Okay, the cutting point here. Okay. So the zeros of the numerators are the positive or negative 2, and the zeros of the denominators are the minus 1 and the 3. So the cutting point of these functions will be the the cutting point of these inequalities will be the minus 2, minus 1, and 2, and the 3. Okay, so then we could find the intervals. Since we find the definition of the 1, 2, 3, 4, which that will belong to 3, 2, minus 1, and minus 2 here, right? And then we could define the intervals. Remember that on the left-hand side and the right-hand side, they have the positive infinite and the negative infinite here. So then we could find these 4 intervals, or these 5 intervals here, okay? And then we could use in the tables and to define the to find these the sign of these functions. Okay, so you can see that we have this 4 point, and then we find this 5 of interval here, right? Then after we find the sign of each of these intervals, and then we will result in this term, and then the totals of this function r of x equal to this term, right? 2 substitute x of this term, right? So you can see that in this case, in these regions, so this term will be the positive. Okay, so you can estimate that in this term, this will be positive times of this region will be the negative. Also, in this case, this will be the negative. Okay, in this region, right? So you can see if I is minus 3, so this also is negative. And also in this region will be the negative as well. Okay, so you can see the positive times of positive, positive times of negative is the negative, right? And the negative times of the negative is the positive. But the negative divided by the positive here, and then that will be the negative as well. So the last row in these regions, there will be the negative, and others are the same. As we see, not the positive, positive, and the negative, negative here, which that will be the positive in this case. Okay, in this region, will negative and positive and negative here. And then since we know the sign of in this region, right? So then we see that if these are the functions, okay, is the function r of x is larger or equal to 0, right? So then these regions and these regions will be satisfied with these rational inequalities. So the solutions of this region will be the -2 and -1, between -2 and -1, right? And also the 2 and the 3, which they will result in a positive of these inequalities regions. Okay, and also you can check in the endpoint, and we see simply to join out of these figures, which that will be the 3, 2, and also this will -1 and -2, right? And then we sketch out of these functions since they have the let me check these functions, which that will be the 4 subtracted of x squared, or we can simply write it down here, which minus x squared and plus 4, and divide by the x squared subtracted of 2x subtracted of 3 here. Okay, so you can see the graph of these functions. This one is the rational functions. And if you still remember the sum of the basic line with the graph here, so this is the sum of the degrees, and you can see the sum of the degrees, and also you can see the degree they have these. Maybe you can see that when we see this 1 divided by x here, so the functions will be looks like this. If you still remember that it's 1 divided by the minus x here, okay. So the graph of this function will be from this term. So you can easy to imagine that this is a sine. So the graph will be similar like this term, right? And also since that is the x squared here, so usually in the x squared here, they will also have this term here, okay, which they will have the intercept of this y axis here, okay. So the domain of these regions will also included of this region, okay. So after we learn some of the basic information from the graph here, and then we could sketch out of the function of the sketch out this function, these rational functions, and then we find the definition of these regions, which that r of x has to be larger or equal to 0, right? So then they will be in these regions, and also in this region here as well, okay. Which that will be a result in between these and also between these regions. Okay. So I think it's quite consistent with our evaluation of these inequalities. Okay. Okay, so that's the sum of the rational functions, and that's some of the polynomial inequality and also the rational inequalities. Okay. So any question on the rational on the polynomial equality and also rational inequalities? Okay, I assume that no, because that's quite fundamental inequalities what we learned in chapter 2. You're just using some of the basic operation with this polynomial function and the rational rational inequalities. Okay. Here we also list some of the practice work, maybe not homework. Okay. Practice work on the this practice in the textbook, so we can try to practice that, which that is quite related to our lectures. Okay. And also that will help you to understand what we learned in the in this chapter. Okay. And if there is no questions, and I think maybe we just continue our next chapters, and we will finish that before 12 o'clock. Okay. Okay, so next section will introduce the exponential and the logarithmic of the functions. Okay. And since we know in chapter 1, we learned in chapter 1, we learned some fundamental, right, of the mathematics. Okay, in chapter 2, we learn some functions. Okay. Okay, some function, the definition and graph of the function, and also the operation of the function, right? And then we know that there are many of the functions and depends on different of the real situation and the physics phenomena. Okay, so then we learn that the CH3 is regarding the polynomial function and also the rational functions, right? And also with its inequalities. Okay, so then we know that the functions we know the functions have input of x, and then we have the functions, and then we will have the output of the f of x here, and then find the solution of the x here, right? And then we learn the polynomial function, rational function in chapter 3. So in this chapter, so we will learn some of the exponential function and also the logarithmic function here, which they in some of the physics they were using this type of this they were using the exponential function or logarithmic function to present certain of the physics or in the real situations. Okay. And usually in this chapter, we are using these exponential functions from which they will have the f of x equal to the 2 of the x, 2 of the power of x here. Or we can know that in the polynomial function that they form the an xn, or we can see that this was p of x, right, in polynomial functions. But in the rational function is the p r of x equal to the p of x divided by the p of x divided by the q of x, for example. Okay. And now the exponential function they are using normally they have the sum of the f of x equal to the 2 power of the x here, for example, where the x was in the exponent of the form here. And in this case, so you can see the f of x here it was based on the 2 power of the x here. And in the exponential function, they could be using a various of these the base, and then they will have a different of the function of these exponential functions. Okay. So in the exponential functions, these functions is like the, for example, in the f of x equal to the 2 power of the x here, and where the independent of the variables is in exponent here. Okay, as we explained. And it usually used to the model of the many real-world phenomena, such as the growth of the populations and the growth of the in investment, and that earns of the compound interest. Okay, and also the decay of the radioactive of the substance here. Okay, and then maybe you can give some example. For example, if you know that the population, the growth of the populations, okay, so that's not a good idea. Okay, not a good example. We just continue some of the electronic devices here, and as we know the some of the IC design, they have the sum of the digit, as we know, which they have. We are using the 0 and the 1 to control the on and to control the on and the off, right? So if the we define that the electronic devices that is on, the on means that the electronic, we can see. So you can see there is a switch, and if the switch is on, so it means that the the switch is connected, so the electron can pass into this one. Okay. If that is off, and then electronics cannot pass into this one, so this will be the 0. So we define that this one is 0, and this was defined a 1 here. So how the computers calculate this? This is the way how do you calculate the computers controls, which that define that is the on and off, or define the 0 and the 1. They are using the 0 to define the off of these computers or the IC, and using the 1 to define the on of this IC circuit. Okay, integrated circuit here. But as we know that nowadays the CPU, or that is the computer processing unit, which that is the just like the human head, okay, the human brain here. I think the human brain, we can easily to control that and to know how to judge or to control the to understand things, right? But the computers, they are using this on and off to define that is correct or that is incorrect, and then to do the further of this correction or identification of that. So usually they according by the development of the technologies, so the semiconductor industry, they could build up many complex of these computer process. They could have many of the, they could control the on and off. They could control the on and off quickly, or and how can I explain that? I think that could be. I'm just trying to use in some basic information to let you understand of this device. So you should know that this is IC, or we can call that CPU. So we know, since we understand the electronic, we're using this on and off, or 0 and 1 to define that. But as you know that in our human brain is very complex, and we could define and know and also distinguish many of things, which that's why human brain is very complex. But in the computers, they are trying to using this on and off to control this on and off, right? And also they could in such of the small of the devices, or the computer process unit here, so they also could control the on and off many of the on and off here, right? Since we know the electronics transportation is very fast, okay. And also within of the one, if for example, if we know that this IC design, the processes, they were using this, and they could find these solutions. For example, if the we also have the X input, okay, we like these functions. They have certain function, then they will have the output. They will have the function. Also, they will have the output, right? F of X here. So in humans, so I think we can easily to find it here. But in the CPU, they also could try to calculate or to find the solution of this function by the defining of the 0 and 1 here. But in the case of if we are human brain, so could distinguish very complex situations. But in the computers, they cannot distinguish a very complex form. They may using the 0 and 1 to control to define that the complex form here, but it takes time to find the solutions here. Okay, in some cases they will have the they always find the, if that is the 0, and then you can go into the next process, which is the 1, or if that is the 1, and then you can go into the next step, which that is on or off, and on and off here. So you can see the computers or the CPU, they have the two choice. So here's the one of choice 2, and then they have the two choice 1 on and off, right? and also in that is a two choice, which is on and off, and also they have on and off here, and also they have on and off here. So you can see that in the CPU they have 1, 2, 3, 4, 5, 6, 7, 8 here. Okay, so they also have the two choice. So and also have the two choice. So you can see the CPU they will have the two power of the 8. Okay, so you can see they are over 2 power of the 8 of the choice for a CPU to make a decisions to the next step or to the next step of these calculations. So that's how the CPU runs. But you can see that it takes times. Not like human brains, you can just distinguish this x input, and then we could find the f of x here. We can maybe one step that we can find the result. But in the computers, they may have to do in this a step to find out. So you can see that's how we find this exponential function, which we could define that is the 2 of the power of x here. Okay, so maybe in some of the functions they may take about a lot of the 0 and the 1, 0 and the 1 and 1, 1, 0 and right here, and then to find the solution of f of x here. Maybe just one of example of the exponential functions. Okay, in the electronic devices. Okay. So now I think that's from the very old of the computers, which they have only a digit here. So now we have the 16 bits and also 22 of the bit. Okay, byte. Okay, and also now even with this 46 of the bit. Okay, of the evaluation. So you can see the computer could evaluate 2 of the 64 times of the processing in a very short time here. So that's the difference of this exponential function could be present. So you can easily to understand that maybe in the very old CPU or the digit of the byte of this 8 bit of the evaluation, maybe 1 times, maybe 1 second, the computer could only calculate about 8 bits of the processing. But nowadays, the computers with such a small of the piece CPU, okay, they could evaluate over 6 power of the 64 of the processings in the 1 second, for examples. So that's the difference of these terms now. So, and this is one of example of the exponential functions. Okay, so there are many types of these exponential function could be present, like the growth of the populations. For example, in the population with these bacteria, and you know, if you still remember, or maybe I explained that before, one of the example of the growth of bacteria, right? So you know that every of the 20 minutes, okay, one bacteria. After 20 minutes, they will grow after 2 of the bacteria, right? Okay, so another 20 minutes. This will be 20 minutes and 20 minutes, okay? There were another 2. Okay, so another 20 minutes. So then there will another of the 2, right? So you can see that after 20 minutes, the cells or the bacteria or the virus, they may could become twice after 20 minutes. So maybe after another 20 minutes will be the twice of the second times here, which will become to 4 here. Okay, so then you can see that they have certain phenomena like the this is 1, start from the 1, or we can use in the 2 of the 0 times, and this will be the 2 of the 1 times, and this will be a 2 of the 3 times, second times, and this will be a 2 of third times here. Okay, so then they will have certain of the phenomena like the we can assuming that these functions as the f of x equal to the 2 power of the x here. Okay, where the x will be start from the 0 to the, maybe you can imagine that maybe after maybe 1 hour, 2 hours, maybe 2 hours. Okay, 2 hours means that 120 minutes. Okay, so then maybe every 20 minutes, so that would be 6. We can estimate that after the 120 minutes, then what's the f of the amount will be. So you can see that will be the 120 divided by 20, which will be 6 here, which they will be have the 6 times of the variation. So then will be the f of x when the x equal to 6, f of the 6 here. So then the 2 of the 6 here will be the 1, 2, 3, 4, 5, 6 here. Then will be the 64 of the bacteria compared with this one. So after 2 hours, there will be the 64 of the bacteria or virus or the cells will be grouped after 2 hours. So we can see that this talking about discussing about the populations of this function, or some of the population with this different of the cells or the bacteria or the humans. Okay. Okay, so that's some of the example of these exponential functions that could be using in some of the real situations or some word. Okay, but this one is close to the 2 times of this term. But in some case, they will see using the different of the base. For example, 1/2. Maybe you can see that the base. If you are using the 1 divided by 2, that means they will decrease every of the certain of the time, right? And then you can see find the situation or phenomenon of this exponential term here. Okay. Okay, so this how we explain the some examples. Okay, of the exponential function, right? So this just gives some basic examples of the 2 power of x here, where the 2 means that is the base of these exponential functions, and the base could be any of these term, which that could be a 2, or could be any of the 2, or any of numbers, any of the real numbers could be present the base. Okay. And the x here just will be in the exponent term here, which that depends on the how much base you are here. So in the case of the f of x equal to 2 power of x here, so in the case of the f of 3, which that will equal to 2 power of the 3, which will equal to 8. In the case of the 2 power of the 10, and then will equal to 1024. Okay, in the case. In the case of the f of x equal to the x equal to 30, so that means the x equal to the f of x equal to the 2 power of the 30 here, which will be the more than a billions of these numbers here. Okay. And if you compare the sum of the polynomial function g of x equal to the x squared here, where the x was in the base here, which that g of the 30 when x equal to 30. Okay. Then g of 30 will equal to the 30 power of the 2 here, okay, which will equal to 900. Okay, so you can see compare with this exponential term. The f of x will equal to the 2 power of the x, and g of x will equal to the x squared here. So you can see that in the beginning, so it's not clear to see the difference. But if you see that when the x is equal to the certain of the amount, for example, like the 30s, you can see the function, the exponential function will be very large numbers after doing this term when the x was in the exponent. But when in the case of the g of x, they only will result in the 900 here. So you can see that the difference of the x was at the exponent and also at the base here. Okay. So the point is that when the variables is in the exponent, and then even small changes in the variables can cause the dramatic changes in the value of the functions. Okay. So in the exponential functions, and to study the exponential function, we must firstly define what we means by the exponential expressions a power of the x when the x is any of the real numbers. Here we define the a power of the x for a is larger than zeros, and the x is the rational numbers. But we have not yet defined the irrational powers here. Okay, so what is mean that by the phi power of the square root of the 3 and or the 2 power of the pi here. And to define the a power of the x when the x is irrational, and then we approximate the x by the rational numbers. For example, if the square root of the 3 is approximately equal to 1.73205, and then the irrational number is an irrational number which they have the no of n of this the decimal numbers here. Okay, so we successfully approximate the a power of the square root 3 by the following term here, which we can see the will be approximately a power of the 1.7 or the original a power of the square root of 3, right? It also could present that it could be presented the a power of the 1.7, and or it could present out a power of the 1.73, etc., and so on. Okay, with the difference of the decimal. Okay, and we can see that these rational powers of the a are getting closer and closer to the a square root of the 3 here. In the case if we are using the more of the decimal of these numbers here. And then it can shown by this using this advance of the mathematics that there is exactly one numbers that this power of the approach is here, and then we define the a power of the root square of 3 to define these numbers. So in the case if we have the numbers the base of the 5 square root of 3, which is approximately equal to the 5 power of the 1.732 here, which will be approximately equal to the 16.2411. Okay, and this will be you can using these calculators to find it. But now I think this will be the square root here. But you can also try to use the find square root of 3, which will also equal 5 square root of this 2 3 of the 1 divided by 2 here, right? Then you can simply know the you can find that start from this square root if you know that the square root of this term, but either from the 3 first of the 1 divided by 2, or you can using this 5 1 divided by 2 of the 3 times here, and then to find to approximately to find the result of this square root of this term by hand. Okay, but you can also try to using the calculator to find this the solutions of this exponential function. Okay, and as we learned that the more of the decimal place of the square root of 3, and then we could use in our calculations, and the better our approximation of these numbers we can get. Okay. Okay, so here we define the exponential functions, where the exponential function with the base of the a is defined for all the real number of the x by the f of x equal to the a power of the x here, where the a here is the larger than zeros, and the a cannot be the 1 here, since if you know that f the 1, no matter what the x is, and then the f of 1 will equal to the 1 always. Okay, no matter how the x. Okay, so then it will be how x here. So the x could be any of the numbers. Then f of x will equal to 1 always. Okay, so and in the case of this term, so a cannot be the 1. So because there's no further meanings on that. Okay. So here are some examples of the exponential functions. For example, f of x equal to the 2 power of x, which is the base of the 2. G of x is equal to the 3 power of x, where the base is 3 here in the case. When x equal to the h of x equal to 10 power of x here, which is base of the 10 here. So you can imagine that when x equal to 1, then the function f of x will equal to 2, and g of x will equal to the function will equal to 2, and g of x will equal to 3, and this will equal to 10, right? When the x equal to 2, and then f of x will equal to 4, and the g of x will equal to 9, and the h of x will equal to 100 here, which that will equal to the 2 times of the 2, okay? And x means that you can see it's on the exponent. This will equal to 3 times of 3. This will equal to 10 times of 10 here. So you can see when x equal to 5, okay, imagine that this will be 5 times, which will be 32, okay, which that will equal to times of 2, times of 2, times of 2, times of 2, okay. And then when this will equal to 2, and then the power of 2, x of 2, 3x here, which and let me check this one. And there will be the A91 here, okay, right? Okay, assuming that is correct, okay. There are 3 times of 3 times of 3 times of the 3 times of 3, okay. This will be the 9. Okay. No. 9. Okay, so this is not correct. Okay. B3.
Maybe 243.
Yeah. Okay, that's correct. So yes, that's great. So that's the 242, right? It's 3 times, right? Okay. So in the case of this x equal to 5, so the base of 10, so we can see that will be the 1, 2, 3, 4, 5 zeros on that here. Okay. So you can see the changes of the different of the base. they will also affect the value of this term here. So these also are based on the real numbers here. But in some cases, when a was a usually a's cannot be zeros, right? Cannot be equal to 1, and also a is larger than zeros. In the case of the a was between the 0 and the 1 here, they will also have the difference of the meaning, which that will be decreasing. In the case of the a larger than 1 here, okay, larger than zeros, or when a larger than 1 here, then the function or the exponential function will increase. Okay. Okay, so here maybe we just finished the maybe these just some examples. If we have the function f of x equal to the 3 power of the x here, where the base was on 3, okay. So then f of 5, we just explain that there will be 2, 4, 3. We're just doing that. Or you can use in the calculators. We simply know the 3 times of the 5, and then with the maybe not 3 times of 9. Because in some in the scientific calculators, they have certain of the functions with the exponential of the x here. So they will have this icon or this term here, and then you can simply type the 5 or the 3. First, you type the 3, the base, and then type this icon, and then you and place of the 5 here, which that will present that in a 3 power of the 5. No. Yeah, 3 power of the 5 here. Okay, but that's some of the scientific calculator. They have certain outcome, or in the computer or in the computers, they are using these symbols to present the exponent, okay, which that means that this also shows the 3 exponent of the 5 here. Okay, then enter, they will get the result. But that depends on different of the calculators. And I think many of the calculator, they are using this icon. You can try to put this up. Okay, so in the case of the minus of the x, and then this will be the 3 power of the minus 2 divided by 3, will approximately in this region. Okay, and also the f of the pi will approximately equal to 31.544, and f of the square root of 2, which will approximately equal to the 4.7288 here. Okay, so you can see they are using this term. It's the exponent of this certain of the component. Okay. Okay, so you can see the result. So I think the functions f of x will equal to the 3x here. So you can see the x could be any of the real numbers. Okay, could be the positive or negative number here. But if you are familiar with this, the operation of the mathematics, so this will also quite interesting or quite easy to understand. That is in the case of the -2 divided by 3 here, which will be 3 power of the 2 divided by 3. And you could present that into the 3 power 1 minus 1 first, okay? But that would be the minus 2 times of the 1 divided by 3 here. Then you can doing this one, maybe you can even with this 3 minus 1 times of 2 times of the 1 divided by 3 here. Okay, so you can choose the convenient way to find the solution first here. Okay. For example, if you are using this 2 case here, so then you would simply know that that will be 9 here. Okay, then you can see square root of 3 of the 9 here. Okay, you can approximately find the result, which will be 0.4807, etc. here. So I think that's the way you can easily to find it. Okay, so since we understand the exponential functions, and then how we find this graph of the functions. So we first the graph of the exponential function by the point plotting as the function as the graph of the function, right? For example, if we the function f of x equal to 3 power of x, and also x equal to the g of x equal to the 1 divided by 3 of the x power of x here. Then we are using the point plotting here. So as we are drawing by the point plotting, we list of the tables which x and the function f of x and the function g of x here. So in the case of the when x equal to 0, in the case of f of x will equal to 0, and g of x will equal to 0 too here. So you can see that this will be the 3 of the 0, which will equal to 1, and the 1 divided by 3 of the zeros. We know that is equal to 1 as well, right? So when the x equal to -1, -2, and then -3, the f of x will equal to the 1 divided by 3, 1 divided by 9, and 1 divided by 27, which you can see that is 3 minus 3, 3 minus 2, 3 minus 1. Okay, so that's quite makes sense on this term here. And when x equal to 1, 2, 3, then will be 3 power of the 1, 3 power of the 2, 3 power of the 3 here. So that's quite makes sense on this one. And in the case of this g of x, so then when the x equal to -1 here, which that will present that in the 1 divided by 3 of the -3, right? So in the case of the 1 divided by 3 of the -3 here, which will equal to the 3 minus 1 times of the -3 here. Okay, so this will be the 3 minus 1 times of -3, which will equal to 3 of the 3, power of the 3 here, right? So then it will equal to 27. So that's why it makes sense. We go equal to 27. Okay. So others the same. So in the case of the x equal to 3, so then this will be when x equal to 3, then 1 divided by 3, x equal to 3. So that quite easy to understand. That will be the 3 times of the 1 divided by 3. Then we will equal to 1 divided by 27. Okay, in the case. So then we just plot out of this the graph of this f of x and the g of x here. So you can see f of x will looks like in the red colors, and also the g of x will looks like in the blue color here. Okay, you can see that, and since that you can see clear to see that the g of x will be the reflection of the f of x with this y-axis here. Okay, so you can see that in the case of the g of x, f of x and the g of x here, so you can see that g of x will equal to the 1 divided by 3 here. That also could present that the 1 divided by 3 of the negative exponent of the x here, which will equal to the 3 and the minus x here. Okay, you can also present that 3x of the minus 1. Okay, so then you can see that since that the 3 part of the x here is the function of x here, so then it will be f of x of the minus 1, which present that 1 divided by the f of x. So you can see that is quite interesting of things that the g of x is the present that is 1 divided by the f of x here. So you can see that it's quite similar to understand, quite similar of the graph, but reflected with this y-axis here. Okay. Okay, so you can see the x present that is the 1 divided by 3 of the x, and then in the case you can see equal to the 3 minus x here, and also present as f of the minus of the x in this case. Okay, you can see it's 1 divided by x as well. Okay, so we could find the we could have obtained the graph of this g from the graph of the f by reflecting in the x, the y-axis here. Okay, so the same we can try to practice some example of the exponential function here. So since we have practiced the y equal to the 3, and we find is the y equal to the 1 divided by 3 of the x here. Okay, so you can try to find the y equal to the 2 power of the x, and it will from here. Okay, so in the case of the y equal to power 10 here. So from the previous example, we know that the when x equal to the when the base, we can see that the base, which that will be 2, this will be 3, and this will be 10 here. And as we learn that the function f of x, the larger of the base and the function will changes rapidly. Okay, so you can see the when the base is equal to 10 here and the power of the x, so then they will close to this direction, which you can see one of the same of the 1x here. Okay, so here will shows you the f of x. This will be the 2 of the x here, and this will be the 3 of the x, and this term will be a 10 of the x here. So you can see it quite makes sense that the larger of the base, and then the numbers, the result of this function will be higher. Okay, so in the case of the a was between the 0 and the 1 here. So you can see start from the 1 divided by 2 here. So and you can see the larger of the numbers, and also the larger of the base, or the smaller of the base, and the function or the result of this function will also increase higher, because you see that when the x gives the power of the x here, okay, so when the x approaching to these zeros here, and also you can see the base of these functions, and the larger of these base functions, and see the because that is the one divided by the numbers, but numbers you can see if that increases, if that number is increasing, but you can see that the x numbers will start to decreasing to the approaching to this 0 term. Okay, we can see when x approaching to the zeros, and the function will also is increasing here. You can see compare with this 1 divided by 2 of the x here. And also in the case of this 1 divided by 10, and then x here. So if you are using the sign of the 1, x equal to 1, for example, so you can see that that will be the 1 divided by 2, and this will be 1 divided by 10 here, which that will be equal to 0.5, and this will be equal to the 0.01 here, the function here. So you can see with the one of the result, in this case, in the case of the 1 here. So then this will be the 1 divided by the 2, and this will be the 1 divided by 10 of the x here, the same of the x here. Okay, so this is quite not consistent with this one. Or when x equal to 1, and when x equal to this 1. Let me check. Assuming that this is the 1 here, then this will be the y equal to the 1 divided by 1. Okay, then this 10 should be y equal to 1 divided by 10 here. Okay, so that's quite strange on this term. If you are using this the same of this x here, okay. So let me check which part is incorrect of this term. Okay, so when x equal to 1, so that 1 divided by 10, divided by 10. This is not a 0.1 here. This will be 0.1 in this case. So that's the f of x, f of the x equal to 1 here, to 1 here. In the case of this term, and also in the case of this term. So this is supposed to be okay, because that's a comparison with these two examples. So if that x equal to 1, and then f of the 1 divided by 10 will equal to the 1. And okay, because this is not equal to 1, so this will be equal. I mean, so on the left-hand side of this term, this will be the -1 here, right? You can see this will be at the left-hand side of the 0. So the x at this term here, this is supposed to only apply this x is less than 0 here. So in the case of this, it will be the -1 here, okay? -1 here, okay? So then the f of the -1 here, you can see that this will be a -1. Then this will be 2, -1, right? This will be the -1. Okay, so we can see that that will equal to 2. Okay, so then this will equal to 10 here. Okay, so that's the exponential function when the base was between the 0 and the a was between the larger than 0 and between the smaller than 1 here. Okay, so that will make sense on this term when the we have this function here. But I think that's will just depends on you how you graph it out of these functions and graph it out of this exponential function here. Okay. So and also the graph of this exponential function or any of the functions, and you can just simply using the same of the operation with mathematics. Okay, and then you could find the graph of this function, and then to define the point on the xy coordinate plane. Okay, so you can see just find that this will be the -1. Okay, in this case, because you see that this function was reflected with this y-axis, which that will be this part will be the negative sign, okay, of the x, and the x here will be the positive. I think you can see that based on the zeros. Okay. So all these graph passing through this point of the 0 and the 1 here, since we know the base f of x, the function f of x was some a of the x here, where the a we know that when the x equal to zeros, and then the f of the zeros will equal to the a of the 0, which will equal to 1. Okay. Okay, so because we know a of the 0 equal to 1 for a is not equal to 0, and you can see that from these figures, and there are two kinds of the exponential. So you can see when the a was between 0 and 1, the exponential function will decrease rapidly. Okay. When the a was larger than 1, and then function will increase rapidly here, which will be the here regions will a larger than 1. When the a was between 0 and 1 here. Okay, so the graph will be similar like this time. And also you can see if the case of the function, the base was larger than 1 here, when the x approaching to the infinite here, the functions, the y or the f of x will approaching to the infinite as well, and also rapidly. In the case of this a was between the 0 and the 1 here, you can see when the x approaching to the infinite here, so they can also see that the functions will decreasing of the rapidly. Okay. Okay, and the x-axis is the horizontal asymptotes for the exponential function f of x equal to a power of the x. And this is because when the a is larger than 1, and we have the x, a power of the x approaching to the 0 as the x approaching to the negative infinite. And when the a was between the 0 and the 1, and we have the a power of the x, all these functions approaching to the 0 as the x approaching to the positive infinite here. Okay, x approaching to the positive infinite. Then you can see that the f of the when a was between the 0 and the 1 here, then the function will approaching to the zeros. It's how we explained that in the previous section of the previous slide. Okay, so the a power of the x larger than 0 for all the x was belong to the any of the real numbers. So the function f of x equal to the a power of the x has the domain of the R and the range of the region, which from the 0 and infinite here. From these figures, we can see the graph of these exponentials functions will, as we define that f of x equal to the a power of x, where the a was larger than 0 and the a was not equal to 1 here. So the domain could be any of the real numbers. Okay, and the range will be always the y was always larger than zeros. Okay, and also the range will be start from the zeros. Okay, between the zeros to the positive infinite. Okay, so here is the example. If we have the graph of these functions, and find the exponential function of the f of x equal to ax, where it has passing through this point here. So we know that this is the x, and then this will be f of x here. So since we know that the x, f of the 2 will be 25, and then we know that there will be certain of the term, which the x here will be some numbers of the 2 here, okay? So then we know that the a will equal to 5, since we know that the 5 squared here will be 25 here. Okay, so the function here, we just simply know that the f of x will equal to the 5 x here, okay? In the case of these two, 3 and 1 divided by a here, so f of the 3 will equal to 1 divided by a, and we know this is some numbers of the 3 in this case, okay? So we can see that the a will be, know that it will be the 1 divided by 2 of the cubic here, since we know that 1 divided by 2 times 1 divided by 2 times 1 divided by 2 here will be 1 divided by a here. So we know that these functions will be the f of x equal to the 1 divided by 2 of the x here, okay? Yes, that's what we find it here, okay? Okay, so let me check this one. So the next section, just this part here, this example just would like to show you the comparison of this functional f of x equal to the 2 power of the x here, and the g of x equal to the x squared here. So since you can see that x was in the exponent, so this will be the exponential function, and this will be the polynomial functions. So you can see from these polynomial functions, you can see the exponential function will increase rapidly with a certain of this term here, and on the g of x will rapid. Also, they will increase in, but they increasing slowly here. But if you look into the detail of this term here, you can see that in some parts they will be the polynomial function will increase in faster than the g of x. But when the x was smaller, okay, between these, you can see in these regions, 2 and 4 regions. Okay, so I think that that's some part of the some introduction of the exponential functions. So I think now it's almost 12. So maybe we will stop from now. And do you have any questions on today's sections? Okay, so if not,
Professor.
yes, no. Okay, so if not, okay, yeah, no, if not, maybe we just stop from now, and we will continue the following sections next week. Yeah. Okay.
Okay, Professor.
Okay, so let me check. Okay, so so if not, maybe we just say goodbye. Okay. Yeah. So I will see you next week, and if you have any questions, so just let us know. And so have a good day and have a good weekend and have a good holiday on Mondays then. Yeah. Okay, see you. Bye bye.
See you, Professor. Bye bye. Have a
Okay,
nice
bye.
weekend.
Bye.
Bye, teacher.
Bye bye.